Hi and welcome again. Today we're talking about binary trees in the array representation. So let's go straight into it. Well, a binary tree is responsible for storing data. It is a data structure and it is very efficient for searching data. There are a lot of improved versions of it, mainly AVL, which has some height conditions to the tree, and a BST, a binary search tree, which says how the elements in the tree should be ordered. And we can see a tree as an extension of a list because it doesn't have one pointer to the next element. It usually has pointers to the children elements here in a binary tree to the left and the right element. Alright, let's define the tree quick. So we say every tree has a node, and that is the root node. And then every root node or every node has two children. And that is basically our tree. And we can there say recursively that every node in the tree is a binary tree by itself. So what does it mean? Well, if we have a look here, then we have the root node 1 and we have the children 2 and 3. And here we say that is a tree. But also, the 2 is a tree by itself with its children 4 and 5. The 2 is the root node and 4 and 5 are the children. And the same holds here for the 3. It has the children 6 and 7. And there's one more important thing to say, that there are no circles in a tree allowed. Because that would, for example, mean that there is an edge from 5 to 1, and then we would have the circle 1, 2, 5, 1, and that is not allowed in a tree. Alright, so let's have a look at the array representation. If you want to have a look at the list representation, where we have the pointers to the children elements, you can have a look at the video that I put in here, up there somewhere. And but for now let's have a look at the array representation. So we basically do a breadth first search in the tree, meaning we look in the first layer here, that is the 1. So we take the 1, then we write down all the children of this node. So we have 2 and we have 3. Alright, and then we write down their children, and also again from left to right, and that is 4, 5, 6 and 7. Alright, so how do we get to the children then? Well, we know the first node, it is the 1. It has the children 2 and 3, so we draw some arrows there. That are the children. And then we can have a look further. The 2 has the children 4 and 5 there in this array representation. And the 3 has the children 6 and 7, which are there in the array representation. And what else do we see? We see that our first layer, the layer 0, has exactly 2 to the power of 0 elements. The second layer has 2 to the power of 1 elements, and the third layer, layer 2, has 4 elements. That's 2 to the power of 2. And we have exactly the same in the tree representation. If we look here, there we see also that every layer has this amount of elements. And that helps us a lot if we index the tree in the array representation. Let's write down the indices of our tree elements. The 1 has the index 0 in the array, the 2 has the index 1, and so on. So what we can say now is that our first child is always 2 times the index of our current node where we want to have the child from, plus 1. And if we look somewhere else there for the 3, the first child is a 6, so it holds the same for it. And the second child is then 2 times the index of the current node plus 2. So what does it mean? That we can traverse our tree using these indices. And there's one more important thing to say, and that is that a node is a leaf node if 2 times the index of our current node, 2 times the index plus 1, is longer than the length of the array. Alright, so with that, we can have a look at the breadth first traversal of the tree, and that is kind of easy if we look at the array, because it is simply our array. So we are done with that. That is kind of easy. But let's have a look now at a little bit more advanced technique in the array representation, and that is the depth first search or the depth first traversal. Okay, so what are we doing? We have basically a result array, and we go through till we are at the first leaf node, and we go through it from left to right. And if it's not a leaf node, then we have to keep going until we reach someone, and then we go a stage ahead. But let's have a look at the picture here. Alright, at first we are at our root node, and we go to our 2. That is our first child of the root node. And from there we go further, because it's not a leaf node, to the 4. Alright, the 4 is now a leaf node, so we can go back to the 2 and we can store the 4 in our result. Alright, now we have a look. Did we work on all children with the 2? Are we done with the 2? No, we are not. So the 2 has another child, so we have to go to the 5. There it is, the other child of the 2. And from there we go back to the 2, and now we see we are done with the 2. We worked on all of the child nodes of the 2, so we can put the 2 also in our result list. So what we have for now is 4, 5, 2 in our result. Alright, from there we are done with the 2. We go one stage previously, or previous to the previous stage. And there we are at the root node 1 again. Alright, so are we done with the 1? No, we still have child nodes of the 1 that we didn't work on for now. So we go again to the 3 now. And there we have a look. Is it a leaf node? No, it's not. Are we done with it? No, we are not. So we go to the 6 from there, and that is actually the first child of 3, and it is a leaf node, so we can put it in our array. Alright, from there we go back to the 3 again, and then we check again, is the 3 done, or is it a leaf node? No, it's not. So we go to the 7, that is the last child of the 3. So it is a leaf, so we can go back to the 3. And then we are done with the 3, so we can also append it to our results, and we can go back to our root node. Now all children of the root node are done, so now we can also append the root node. So what would be the result of this depth first traversal? It would be 5, 4, 2, 6, 7, 3, and in the end the 1. Alright, so let's implement that in Python. At first I create a new file called binary tree as array, and there I create a class binary, capital letters, binary tree as array. Alright, and in there I have a property tree, which I initialize at none. So we just have the empty tree. Let us implement at first the breadth first search. So we say def bft, breadth first traversal, and it has just self as a property. And there we say a little documentation commentary. And we say breadth first traversal of the tree, and let's say here we call that BFT, as an abbreviation, and we say returns an array of the tree in BFT order. Alright, and the only thing we have to do here is we have to return our tree. Oh. Alright, so far so good. That was the breadth first traversal already. So let's go now through the depth first traversal. So we say def dft, and there we say also just self, and we say depth first traversal in brackets dft, so everyone knows what is meant of the tree, and we say returns an array of the tree in DFT order. Alright, so let's implement that. At first we need a queue, and what we store in that is our indices of the elements in the tree, because we just work on the indices and not on the actual elements. So since we start with a root node, we can add the 0 here for the index 0 already in our queue. That is our root node. And then we need a list for our result. Alright, so good so far. What we do now is we go through all our nodes, and we do that until our queue is actually empty. So we say until the length of our queue is bigger than 0. So here we say until queue is empty. And what we do there is we at first get our current index we are working on, and that is q0. We always take the first index in the queue, because we will also insert the elements we are working on in that order. Alright, so, and then we can already say we are working on that, and once we are done with working, we can remove it. So we can also write it here straight away underneath. We work on the node and remove it, therefore. Alright, so what we have to do now is we have to add the children, but we also have to check if the children exist. So we say add children to queue if exist. Alright, and how do we do that? We use a for loop here for child in, and yet let's say range 2. That gives us, no, we actually need the numbers 1 and 2, so just let's do 1 and 2 here, so to make it more obvious. So our child is now 1 and 2, and we can make use of our index representation, where we know that every child of our current node is on index 2 times index plus 1 or 2 times index plus 2. Alright, so now we check if the child actually exists. So we can say if 2 times the current index plus the child is smaller than the length of our tree. And here we have to use self.tree. Then we want to add it to our queue, and we want to add it in the first position. So we say our queue dot insert, and there we insert now our we want to insert it at position 0, and we want to say we want our index here, and that we want in 2 times the index plus our child, because that is the actual index of our child. Alright, And when we are done with it, we are already done with working on our node itself. So we can say here, we can add the node to our result. So insert, and where do we want to insert it? We want to also insert it on the beginning. So we work at first on our root node, that is a 0, we insert that. Then we work the next on our node 1, or at the index 1, and we are going to insert that also then on the 0, and so on. So we say here insert 0, and there we say index. Alright, and that should be it already. Now we just have to return our result after our while loop. So let's check if that works. Sorry for that. If name equals to main, so we jump in our main function. There we create an instance of our tree class. So we say binary tree as array. And there we create some data points now. Let's say we use the data points 0 as our first node, 1, 2, 3, 4, 5, 6 and 7. And let's actually not start from 0, so we see the difference between the indices and the actual values of the node. And then we say now at first print, and there we say our bin tree dot, and we want to do our depth first traversal, and we print that. And afterwards I want to print the actual values. So we go through it and say for I in range, and there we say data, or we say actually the length of our data array. And we print our we can store here, let's store here our bin tree, our result, in a result variable, and then we can print here result, so we don't have to do it all the time. And here we say result I, and what we wanted, and that gives us the index of the current element. And so we say there we want actually the data point responding to the index. Alright, so and that should be fine now. Let's print that. And we say here type none. None type has no length in line 30. So let's have a look at line 30. Alright, and here we have self.tree. And that is also important because we have to check here before if the tree is empty. So we say if self.tree is none, then we want to return none. And let's add another thing here. Maybe we deleted some elements from it. So we can say if the length of self.tree is smaller than 1. And it says it wants, we have to say here or, and then it works. And here we also have to set the tree property of in our instance. So we say bin tree dot tree equals to our data, and then it should work now. And if we have a look, we have the index 3, the index 4, which is here. If we look 0, 1, 2, 3 is the first one we print, then it is the leaf node, then we have the 5. Then we have the 1, that is our 2. Then we have the 5 and 6. That are these two indices, 6 and 7. Then we have the 2, that is our 3. And in the end we have the 0, that is our 1. Alright, and if we have a look at the elements itself, our first children are the 4 and the 5. Then comes the node 2, which is a parent of 4 and 5 and the first child of the root. Then we have 6 and 7, which are the children of 3. And then we have the 3, which is the second child of our root node 1. Alright, and that is the depth first search in the iterative version. And I probably go and make other videos on the recursive version too, so stay tuned to it. And you can also have a look at my video about binary trees as a list in the list representation, because we don't have to fiddle around with all the indices there. And it is a little bit a different structure of the tree, but it's also very nice to have a look at that. Alright, so if you liked this video, if it was helpful to you, then give it a thumbs up and subscribe to the channel to always get informed whenever I'm uploading new stuff. I would really appreciate if you write me down in the comments below what you think about the video, what you think that I can improve, or what you maybe want to see in this channel. Alright, so that's it. Have a great day. Bye.